Welcome to a new test and teardown video. This time it's another one of those Danbridge high voltage non-destructive isolation testers. This one is the JP15, so it goes to 15 kilovolt, and it is looking very much different from the other two models I previously made videos about. And I actually also ended repairing them, and we're still using them and we're still happy about them, so all that is perfectly fine. This one is a much more new and updated version compared to the previous videos. And yeah, I think the oldest schematic we can find about JP15, that is from 1989. And the latest is from 2008. The manual you can find on Peel. It consists of many of the different versions of JP15. And it also shows the 1989 and 95 and 2008 schematics as far as I can see, right? This one we think is not working. And we got a few things. The cable with the remote switch and the high voltage port is obviously missing. It is not possible to buy this as a spare part from Danbridge. So if you lose this, you lose everything, right? Probably there's another way to fix this, but first of all we need to see, is this working? I think the schematic is very similar between JP12 and JP15, because I previously repaired a JP12 using the schematic from JP15, and that worked out quite well. We did figure out what was wrong, and it is of course up and running. This one is the right version for the documentation we got, so that is great. It's the circuit board and everything is completely different between the 12 and the 15 versions. And this one is much more nice and compact. I really like the layout and all that. It's, yeah, quite beautiful. And on the back you can see there's another connector here. This one is of course so you can run this on an external DC 12 volt supply. And they've been really nice and friendly to tell the range. And this one is of course for lead acid batteries. There's a nice big heat sink, external mounted, and I don't know exactly what is the idea here. Maybe we're missing some feet or something that's supposed to be screwed in here. So see, you cannot really stand it. Nope, it will be standing on the heat sink, and it looks like the heat sink is probably isolated or something. It's standing a little bit like that. Well, first so of course let's open and investigate. Oh, that was difficult. I think it's not supposed to be this difficult. I don't know exactly what I'm doing wrong. But we got a groove in the top and the bottom lids. And this kind of bites into the front like really crazy. There isn't any tolerance. So when you try to pull out the chassis, it will always go like that, right? And then it's impossible to pull it out. So you need to grab each side and then pull a little bit like that and bend it a little bit. But it's really thick as well. So that was difficult. And there's another little thing. Can you see the little scratch marks? Here we go, right? And those are intentionally made because they got some little metal sticky thingies on each side of the chassis. And the idea is, I don't know if they stick up right there. So the idea is to give you a bulletproof connection. So the chassis is of course connected to the frame and everything here, and that is of course earth protected, because this thing here is a really crazy high voltage generator, right? 15 kilovolts, and you don't want to touch this in any possible way. So they're really trying to protect you. It is, like I imagined, so much more modern and beautifully designed. I totally love it so far. Let's see when I get a little bit deeper into it. Here is, of course, the control circuit. That will be the push-pull FETs, and there's a little IC that drives these and all that kind of stuff. And we should also find a relay that turns on and on the enable signal. In the previous versions of this control board, the relay also disconnected the 12-volt drive to the IC and the FETs and everything, so it was a little bit more safe. The more modern boards, they only disconnects enable. So that means you cannot really trust that, can you? I mean, I'm not going to touch anything anyway, but I feel the disconnect the supply is a little bit more bulletproof and more safe method. I will of course try and open this a little bit more. Yeah, we need to go and get access to the high voltage. This connector here is like a really long Teflon isolated thingy, and it goes, see, all the way into the goodie box down there. So nice, good mains transformer, little rectifier, some fuses, and all that is super duper pretty. We got a little connector here, so that means we can take away the entire rear part stuff. That is what I think we can do here. And that is, of course, the on-off switch. Oh, this is on 12 volts, obviously. So mains comes in, and so that would expect a little idle usage, even if it is powered off, right? This is at least what I feel we got so far. Let's look a little bit more in details on the different parts of the circuits here. So I will of course put in a little schematic of the power supply unit. So we can see we got a little mains filter, the transformer, and the voltage selector, rectifier and capacitor, and a very funky coupling here. So there's a 12-volt regulator and a few diodes and resistors and stuff like that. And this is because they're using the current capability of this regulator as the current limiting source for the battery charger. And we got the two fuses here. They are on each side of the battery, one for charging the battery and one for using the battery. And those two Schottky diodes, that's of course for charging and using the battery so that nothing flows the wrong way. And that will of course be the power supply, external power supply connector. So the output from this power supply goes to SC6. So that is the connector here. And that one goes of course to the mains on-off switch. And then the red wire goes into 12 volt. So here is the HG on board. So that will be the 12 volt entry point. They just called it 12 volt unregulated, I think. So what you see here is a little transformer, 4 diodes, the capacitors, and 2 little regulators and capacitors. So that will be a plus and a negative 12 volt regulated auxiliary supply. And those are of course used for all the fancy regulated things that needs to be accurate and stable. The fun thing is if you look at the schematic, oh yeah, can you see all the errors? It's just full of errors, the schematic. They just copied the positive supply and just magically thought this this could be the negative supply, and they forgot to change all the components and flip the capacitors and change the regulator IC. But in real life, they are, of course, changed, but they just forgot to update the schematic. So I will, of course, send a corrected schematic to my documentary friend of this Peel webpage, where you can find the updated schematic in case we will, we'll publish the updates. We'll see. So the little switch mode supply here, there is behind this inductor, there's a little IRF 530, and this is a flyback converter, and it is in sync with the main converter. So here is the main power converter. So it is half bridge push pull, again with two IRF 530s, and that will be the two windings. Here you go. I mean, that will be 12 volts into those windings, and I don't know, it's five windings, 12 volt. Oh, cool. So, and the reason why I say only 5 is because it's push-pull. So there's a center point, and then you have those 5 windings with 12 volt, and then you have 12 volts the other way on the other windings. So it's push-pull, obviously, right? And yeah, that will be the little safety relay. And on both of those schematics, it looks like there is a connector that goes to the other circuit board. And that is, of course, just this connector. Is this a 1-to-1 over here, this interconnect connector. And it's not super good explained in the schematic what is what. So I was thinking about adding some labels to the different signals for easier debugging and all that. We got quite a lot of trimmers in here on the front panel circuit board, and there's of course a separate schematic for the front panel. See all the different voltage ranges, current ranges. You can of course calibrate the readouts. It looks like this resistor here is nice and fine. And then there's of course a little audio amplifier and filter, and it works by its so you kind of listen to the voltage you test your test object. So that voltage, you can imagine, will start to pull some current spikes when you're near some when you're near the breakdown voltage of whatever component it is. So this generates some AC signals on your high voltage line, and that goes into amplifiers that drives this little speaker here. And you can of course connect your headphones here if you want to do that, or a remote voltmeter amp meter. So the secondary side, the high voltage output side, look how beautiful that is made. Yeah, this transformer here looks of course like one of those from old TV sets, and that is exactly what it is. The same type, and one end of the many thousand windings goes of course to chassis. And then there's of course a wire. I don't understand exactly why this chassis here goes through here and is connected like that. Why isn't this chassis there exactly the same? Can you see what I'm seeing here? So here is a shielded cable, and you're now measuring the difference between this chassis and this chassis down here, and it's directly connected. So that is something I don't understand exactly. We also got the audio output down there with some diodes, and that will be the voltage sense output for the voltage regulation error amplifier that's located down here. And I think we can even look through this fully potted high voltage. Yeah, it's difficult to put in some light. Yeah, see the two white parts, that will be the diodes. And we got all the high voltage capacitors and some resistors right there. And in this shielded box right there, I think I can easier show this with my little mirror. So at least I plan to try and see if I can show this. So down here we go. See, here is a little resistor that goes from the output. So this is the Teflon output. Why is the light so extremely annoying like that? See, that worked. So that will be the Teflon output. And then it comes here from the capacitors and resistors and all that kind of stuff. And here is the voltage sense resistor. And that is, of course, in a little shield all the way. And then there we got the wire out there for the voltage sense point. So let's try and power this up. I have, of course, set it in 7.5 kilovolts. So this is the lowest possible. And also the current is the lowest. And I've cranked down the high voltage. And it should not do anything at all because I don't have the switch in here to begin with. So that is my first experiment. So I will turn on mains, and it is using 0.7 watts. So that is a very, very low idle power usage from this transformer. And of course there is no battery to charge. So now that is unexpected. This one should not lit up. Why are we seeing this? It should not generate any high voltage, and it should not. This is weird, isn't it? Why is the amp meter? So look what I did. I removed the short between guard and chassis, and now my amp meter is not reading anything. So on this model, you're not supposed to have a short between these. That is interesting. All right, so let's try this again. I had some major breakdowns actually, because this connector is a stereo connector, and this unit is specially designed to only work with a mono connector like the left one. So I will now try and see if this little switch here will be the activate switch. So let's turn it on again. And now I can of course plug in the plug and nothing bad happens. I have of course cranked down the voltage. Everything is down, and let's push the little switch and see, it blinks to tell us the output is dangerous. But I cranked down the voltage all the way. So let's hold this. And ooh, can you hear? Aha. So we get a little bit of itsy bitsy voltage. So if this is 500 volts, but I mean, and it's using 11 watts, and we can hear the relay goes. What if I try? No. Let's try the other. So that was 500. if the voltmeter is working. Okay, so now it is using, now we need to use the other volt scale, and of course now 500 volt is only that little output. So there's a voltage feedback, PWM regulation volt something thingy problem. So if we look at the schematic here for the push-pull driver system for the high voltage transformer, the two field effect transistors, let's measure on the two gate signals as indicated here. So as you see here on the scope picture, one of the signals is completely low all the time. So I took and measured on the driver to the two transistors. That one is the 4049, and no signals on one of them, and a lot of signals on all the others. Yes, here it is. The SG3524, I pulled it out of the socket, and what do you know? This one is, I don't know if you can see this, from 1984. That is weird, isn't it? Because this unit is from 1993. So somebody blown this up before and they put in another one that is also defect. That is weird stuff is going on here. So I need to go and get some new ones. So it is a nice new day and we got a little bit of progress. So this one is the one that was in the unit when I got the unit. This is the one with one broken PWM output, remember? And look what just came in, 2 new chips. Well, this one here on the top is brand new, just bought in a shop. And it just don't work at all. Like nothing works at all. Not even its oscillator. And if we look at the schematic, we can see the oscillator part of that chip is driving the other little switch mode system that makes the plus and a negative 12 volts for everything else in this unit. So if this is not working, that means this chip is completely dead, right? So then I put in the other one here, and this is from 1993. And the fun thing is this chip has been soldered. So that proves it cannot be from this unit because this unit uses sockets. But this one, the oscillator works, and my 2 voltages from the other switch mode works. But both of the PWM outputs, they're both burned as well. So they're both low and nothing works. And yeah. So we have a little status quo here and a full stop. I just cannot give up. This thing is driving me absolutely nuts. So what have I learned today? I have learned the old switch mode chip from 1993. It seems to be working, but the driver inverter chip that drives the 2 FETs is somehow affecting the output. So it's probably burned on the input side, not the output side. I just put in a new one. I just measured, I took this out and performed some measurements on this one. And look at that. Now I got both of the 2 outputs running. And I mean, the pulse width modulation also respond really nice to the voltage potentiometer. So I feel I should be able to get this up and running now. So we got kilovolts. And we got all the pulses and stuff. Pretty cool, so that is working. So I dimmed the light a little bit. Let's see if we can see both the scope channels and the voltmeter. I am of course in the lowest current setting and I'm still in 7.5 kilovolt. And now when I trigger my output, it goes like that. And we can see the PWM. I think it's a little bit funny. It's not symmetric like that. But that's probably just the way it is. So can I crank it all the way up? See, 7.5. That is full juice in the lowest. And then let's try the 15 kilovolt with the same setting here. So I think it is, yes, you see. So that is it changes. So that is 10 in that range, and you can also see a little bit higher duty cycle. Let's try and go back and see. Yes, exactly. So that is 10. Oh, there is no more. That is funny. So it will, aha. So it overcurrents, or it maxes out somehow. See, there are many more turns to give, but not more voltage. I hereby announce this unit for completely solved. So it turns out there was a little adjustment and somebody's been poking around with that, and that was the reason for the missing high voltage. And I think it has something to do with the switching frequencies and all that kind of stuff. So let's try and see how it behaves now. So this is 15 kilovolt setting, and hello. And the frequency is 26.1 kilohertz. So that means also the end of this video. So thank you very much for watching, and bye bye.